Welcome to my talk about the technology highlights in our new release Geodik 2022. It is a pleasure for me to present the new Geodik version, and I want to thank the audience for attending this year's Geodik user meeting. My name is Eric Klatt and I'm the CTO of Master Markets, the company behind the software Geodict. Before our team spun off the company, I worked at the Fraunhofer ITWM as a researcher. I hold a PhD in theoretical physics from the Technical University in Darmstadt. Before I start with the technology highlights, I want to point out that the Geodict 2022 release is out now. We recommend to download and test it, as we think Geodict 2022 is the best solution for digital material analysis and design. Furthermore, you can explore all the new features I'm going to present in the following slides. What we mean with digital material analysis and design is shown in the workflow in the slide. It often starts with the import of a 3D image of a real material. Afterwards, the image is analyzed to understand the material and its properties. This step alone can already be very useful. If one understands the material's geometric properties, one can create its statistical digital twin. Having this twin, one can start to design or engineer a next-generation material with improved properties. In this way, Geodic can help to design improved materials faster and cheaper. This workflow will aid me now as guideline to walk you through the technology highlights in Geodic 2022. In this presentation, I can only cover a selection of improvements and new features. In many of the more specific talks of my colleagues, you will get more detailed information. This year we look at first at the highlights regarding the property simulation, which are used in the analyze, the validate and the design steps. It is possible now to simulate 3-point flexural or bending tests in ElastoDict. The nonlinear mechanics simulations are much faster. With the new version, it is possible to track objects and contacts during large deformations. The computation speed for demanding Stokes and Navier-Stokes flow simulation, for example for complete filters, is strongly improved. Battery Lear can do fast and memory-efficient simulation with porous binder now. Direct half-cell battery simulation and complex charging profiles for batteries are possible in BatteryDict. The two-phase flow is strongly improved, allowing, for example, a constant flow rate and forced imbibition simulations. Now I show these highlights in a bit more detail. To allow direct simulation of flexural or bending tests in Geodic was wished for many years. Now with Geodic 2022, such simulations are possible. One can specify the bending loads either as flexural deflection or as flexural force. The result is a flexural modulus, the force deflection curve, and corresponding local displacement, strain and stress fields. On this slide, the flexural test simulation is performed on a laminate structure where the bending in x and y direction is compared. The flexural modulus of the example structure is much higher in x direction because the top and bottom sheet layers are oriented in this direction. The color field shows the amount of plastic deformation in the matrix material for both directions. With Geodic 2022, it is possible to use the conjugate gradient method also for nonlinear simulations. This often leads to much faster simulations and a better convergence of the solution. Here an open cell aluminium foam where the struts can deform plastically is simulated. The simulation results are shown in the video. Comparing the runtimes, one sees that with Geodic 2022 the simulation is 3 times faster. It is also possible now to track the object information during a large deformation simulation. This means that one knows which voxel belongs to which object in each deformation step. Here this is demonstrated for a nonwoven which is compressed by 30%. After the compression, the number of fiber contacts is nearly 2 times larger compared to the uncompressed nonwoven. This means that the material is much stiffer now in that direction. The tracking of objects also allows to study how the shape of the object changes during the deformation simulation. For the Lear solvent Floedict, the new acceleration method Krylov is available. This option reduces the runtime for challenge in flow simulation drastically. Such simulations could be fast flows for complete filters or Stokes flows through low porosity rocks. The reduced runtime is paid by an increased memory consumption. In the default solver setting, this new option is used automatically, but it can be enabled or disabled by the user. On this slide, the effect on the runtime is shown for a tight sandstone. Compared to Geodic 2021, the runtime is decreased by a factor of 5. With Geodic 2022, it is now possible to simulate porous binder also with the battery Lear solver. For the battery charging simulation shown on this slide, this leads to a runtime reduction of factor 6 and an immense memory reduction compared to simulations with the best solver. This means that one can compute much bigger and more realistic batteries with Geodic 2022 than was possible before. It is now also possible to directly charge half cells in BatteryDict. This means one can import an electrode or create one with GrainGeo, for example a cathode with a corresponding predefined script. Afterwards, in BatteryDict, one selects Charge Half Cell, sets the parameters and can run the charging simulation without the need to design a complete battery. So it is much easier to perform half-cell simulations. It is also possible to set complex charging profiles. In this way, one can charge and discharge the battery in multiple steps. In the charging plot, this is shown for a half-cell simulation. However, this works also for complete batteries. For the computation of two-phase flow, we have developed the dynamic pore morphology method to extend the quasi-static approach with a dynamic fluid interface movement. This dynamic method features the following: the computation of non-monotonic capillary pressure curves, the computation of forced imbibition, the consideration of mixed wettability. The method now predicts critical pore filling events as published by Yang et al. In 2016, as can be seen in the animation. Details and validation of this feature highlight can be seen in the presentation of Sven Linden. Here is an example where both the flow solver and the dynamic pore morphology method are used, the relative permeability computation of a huge mixed-weight digital sandstone sample. The sample has 1,500 voxels on each side and thus more than 3 billion voxels in total. The entire relative permeability computation required a runtime of less than 7 days and less than 200 GB of working memory on a 32-core Linux computer. Now we come to selected improvements for the analysis of 3D images, which are also needed in the validation step. The percolation paths and geodesic tortuosity computations are much more accurate. With Geodict AI, you can train neural nets for image analysis. In FiberFind, an enhanced post-processing is available for the identified fibers. To get a more accurate percolation path length or more accurate geodesic tortuosity, the option Optimize Paths is available in Geodic 2022. With this option, the paths are pulled tight after the computation on the voxel grid, resulting in more accurate path lengths. Here, this is shown for a single path, where this option leads to a 4% reduction of the computed path length. The path before the optimization is shown in black and the optimized path in yellow. You have a 3D image and you want to find the cracks in a rock or fibers with a specific shape in a non-woven, or the warp threads in a woven structure, you can do this with Geodict AI in Geodict 2022. Just provide the training data, what often can be done via a relatively simple Geodict script. Train your network, validate the results, and if you are satisfied with the net's analysis quality, apply the net to the images you want to analyze. The example on this slide shows the results of a net which was trained to find the warp and weft thread in a weave. The training data for this net was created with WeaveGeo. Applying the net, the solid voxels get different material IDs for warp or weft threads. Let us continue with the feature highlights regarding material modeling, which is needed for the validation and especially for the design step. One can model foams with triangular struts and specified solid volume percentage now. It is possible to generate grains and fibers with more than one material ID per object. It is possible to generate strut-based lattices and triply periodic minimal surfaces for additive manufacturing in GridGeo. One can directly edit selected GUT objects via the context menu in the visualization area. One can model superquadric particles as GUT objects. In the generation of convex polyhedra, one can match the enclosing object volumes. To easily create statistical digital twins of foams, one needs to model triangular struts. Furthermore, one needs to directly match a given solid volume percentage. With Geodict 2022, both is possible in FoamGeo and was used to create the digital twin of an open cell aluminium foam shown on this slide. The pore size distribution and pore orientation was measured with identified pores in PoreOdict, and the strut diameter distribution was computed with FiberFind. Afterwards, one enters the statistical description of the foam in the FoamGeo GUI and creates a digital twin. Until now, a GUT object, like a fiber or a grain, was restricted to one material ID. With Geodict 2022, this has changed, and multiple material IDs per object with specific patterns are possible. This option is available in GUT-Geo and the GUT Objects context menu. Choose Change Material ID Model and create structures as shown on this slide. Here we see grains with stripes, trilobal fibers with radial stripes, and combined objects where each sub-object has its own material ID. With this new feature, one has countless new options for more realistic structure modeling in Geodict. In additive manufacturing, a given space is filled with a periodic lattice structure. Common examples are strut-based lattices and periodic cells based on triply periodic minimal surfaces. In Geodict 2022, one can directly create such lattices in GridGeo, where 4 examples are shown on this slide. The lattice for a specific application must be tailored to specific performance characteristics. In Geodict, one can create such a lattice and directly compute its properties, for example with ElastoDict, when a specific mechanical performance is required. At the end of my talk, we come to some general innovations which are useful for all steps in the design workflow. It is possible now to freely adjust the units and the styles of all result plots. The main GUI was improved to allow, for example, better measure options in the 2D view. New interpolation options for the volume field visualization are available. The export to Excel via Python is possible, for example, on Linux computers. One can create 3D images from surface meshes loaded in Geodict. We have improved cloud computation options for flexible and unlimited computation. Equations and references are available in many solver dialogues. It is possible now to crop volume fields together with a loaded structure. In Geodic 2021, the plots, for example in the result files, are already very nice, and one has a lot of options to customize these plots. However, with Geodic 2022, we have further improved the customization options. One can freely adjust the ranges and units of such plots. Furthermore, one can change the title, color and style of each graph. The customization of plots can be done on all loaded GDR files of a given command at the same time. One can directly save a plot as image via the graph context menu. After the GDR file is closed, the customized plots are saved in the file. All these steps can be recorded as Geodic macro, and thus the plot post-processing is completely scriptable. Geodic supports different mouse interaction modes. These mouse modes can be selected with the tool buttons shown on the top of the slide. In this way, one can select GUT objects and voxels, draw in the current 3D image, and now also measure distances and angles in the 2D view. If a mouse mode is selected, a corresponding GUI element is opened at the right side of the GUI. This GUI element shows the options for the selected mouse modes. For example, one can choose if one wants to measure a distance or an angle. In the shown image, I measure 2 crane diameters and 2 angles between touching cranes. So with Geodic 2022, it is much easier to manually study feature sizes and shapes in a loaded geometry, for example from a micro-CT scan. In Geodic 2022, we have also improved the visualization. One example is the improved field interpolation. For battery simulations, one has often orders of magnitude lower lithium concentration in the electrolyte compared to the active materials. In this case, one gets a wrong impression of the field values when an interpolation across the material interfaces is done. With Geodic 2022, it is possible now to interpolate per material ID or to interpolate only on the visible materials. This interpolation on visible materials can also be shown on a smooth ISO surface. These options lead to a much more accurate visualization of the field values for cases as described before. On this slide, the new interpolation options are shown for a mechanics simulation, where the stress values in the stiff fibers are much larger than in the matrix. The image on the left shows a classic linear interpolation, which leads to visualized stress values which are too small at the material interface. The interpolation only for the visible fibers gives a much better result, which can be seen in the image in the middle and in the image on the right. Starting with Geodic 2022, a third way to export GDR result files to Excel is available. This option is called Excel Generic Python and creates results like the Excel Generic option. The results of both generic exports look very similar, but the new option has some advantages. No Excel is required on the computer the export is done, so it works also on Linux machines. The new export is faster and more robust as one does not rely on Visual Basic. The example here shows the generic Python export for a Stokes result from Flowdict. To get access to more computer power and to use computation resources more flexible, the cloud is a very useful tool for simulations. With Geodic, one has multiple ways to use cloud resources. Interactive remote sessions are already available for a long time. Since last year, we offer the web-based batch operation together with KaleidoSim, the GeoCloud. This option will be available from the Geodic GUI starting with Geodic 2023. As a new option, we offer the web-based interactive remote session. One just logs in to the web interface, starts and runs a virtual machine instance. Afterwards, one can connect to the virtual machine to open an interactive session in a new tab in the web browser. Now one can run Geodict and use it as you would locally, generate structures, perform analysis and simulation, create images and videos. The project directory is an empty 1 TB drive that you can use for structures and results. For the down and upload of files, one can use, for example, WinSCP. In the future, it will be possible to download the project folder contents directly from the web interface. This is the end of my presentation. I hope I could show you a few interesting technology highlights of our new release. Thank you for your attention.